Hello, welcome to part two of intuitive explanation of a gamma function and why it's factorial like. This is part two. I'd really recommend you watching part one to get a mathematical feel for what I'm getting ready to explain here. But here we're going to show it graphically so you can get an intuitive feel for it here. The gamma function, as a reminder, is an integral from 0 to infinity of this function here. And it's factorial. So if you put in gamma of 3, then it's 2 factorial. Gamma of 10 is 9 factorial. And why is that the case? That's what I set out to explore. So he, 3 blue, 1 brown, posted a tweet that said, does anyone have an intuitive feel for why the gamma function is factorial like? And I spent a couple hours last night doing all this, and I put out my first video of mathematically what I figured out, and then here is sort of graphically. Um, and now if others have done this research, that's fine. This is independent of them. And so what I do is I create a function that we're going to integrate from 0 to 1, and I call it blue in honor of 3 blue, 1 brown. And that's the function we're going to plot. And we're going to need slopes along the way when we calculate triangles. And so this is like just a way to find slopes. And we plot this, and so that's what this does. And I'll post this code in my comments if anyone wants to play around with it. But over here, the red lines are the actual gamma function. It's the function that we're integrating to get the gamma value. And these are for n equal 5 and 4. And this big one is 5, this little one is 4. And then I notice I'm like, how can we approximate that? It says kind of looks like a triangle, but where do you draw the sides? Clearly you start at the mode, which is n-1 compared to the n value. But where do you draw the sides? So I thought, you know what, I'll do it at the inflection point. And that's where it's concave up, and that's the point where it starts to go concave down, and this is the point where it starts to go concave up. So I just drew lines through those points. And then this is a triangle, which is actually very easy to calculate the area of a triangle. It's just the height times the base. And it turns out that triangle is so close to n-1 factorial when you have these integer values. And to me, that was like, wow, that's kind of cool. And then the area here, notice that this area is 3 factorial, and this area is 4 factorial. And so this area is 4 times as big as this. And you can really see that it is roughly 4 times as big. Now, I only have 2 plots on a graph at a time because it gets quite busy. So let's do it for 5 and 6 as opposed to 4 and 5. And one thing I want you to notice here is that we're only going to shift 1. We're going to go from 4 to 5, and we're going to go from 3 to 4. But notice the jump. The graph will be 5 times the area of this one when we calculate it. So boom, and then notice that this is a much larger jump. And so this is 5 from the previous graph, and zoop, now it's much bigger. But what's kind of cool is these triangles, using the approach of the mode and the inflection points, actually gives a surprisingly accurate estimate of the area under that curve. How close? So I have a little program here that generates that. So when n is 4, so the gamma function, we plot it and we calculate the area, and the area is 3 factorial, which is 6. But if we use the triangle, which is actually very easy to calculate, it's 5.8. At 5, it's the exact answer is 24, and it's 23.6. At 6, it's 120 and 118, and at 7, it's 720 and 715. So it's actually pretty surprisingly close. But this also works for odd or decimal forms. So in this plot, we're going to go 3.25, 4.25, and 5.25. And here I'm adding 3 because hopefully we're a little more used to seeing what we get. So here's the gamma function when n is 3.25, and here's the gamma when it's 4.25, and this is 5.25. One thing to notice is that the mode is n-1. So the mode of that is 4.25, one less than this. And so it's the same, even when there's decimals, the mode is n-1. And for each successive, increment of 1, it only goes over 1 and up 1. And that's kind of cool in itself. But when you create this triangle and estimate that area, it's actually really, really close to gamma of that value. It's very factorial like. So this area here, the big one, is that area is gamma of 5.25, and it is n-1, so 4.25 times bigger than the area next to it. And so it's exactly factorial like. And let me do one more plot just for illustrative purposes. We'll go from 7, but that means I probably should increase this. And I want to notice the vertical jumps in the size of these plots. Right? So each successive one, it really ramps up because it's n-1 times the size of the one below it. And so you can kind of see visually why it is factorial like that. And the area of these rectangles are actually also really close too. And let's investigate that. We'll go from 3.25 to 7.25. And so 3.25, the exact gamma of 3.25 is 2.54, and the triangle estimate is 2.44. The exact estimate of when it's n is 4.25. It's they're really close. I'm not going to go through all the values, but you can kind of see that they're all very close. And this works for any fractional value. The plot is n-1 times larger than the previous one. Let's go 22, and let's go 8, and that's really going to ramp it up. So we probably should increase our right axis. And look at this jump. For each successive one, it jumps up. So the area of this is, of course, gamma of 8.22, but it is 7.22 times as big as the area of this one, and that's why it's factorial like. Yep. Well, anyway, that's all I have for this video. Hopefully you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.